So let's talk about this sample space for a regular six-sided die again. And this time I'm going to roll this die, but I'm not going to tell you what happened. I'm going to peek at it, and I will tell you that the result is not 6. So I'm going to ask you, what's the probability the result was larger than 2? And you know that the result of the roll, assuming you trust me, is not 6. So how do we do that? Well, let's define an event n for not 6. So I'm going to write down all the outcomes in here that are not 6. So I'm removing the 6 from my sample space. Think of it that way. I know the result is not 6. And now I'm asking you for the probability some event occurs. The probability the result is larger than 2. So I'm going to write the event L, which has all the outcomes, that are larger than 2. I said larger than 2, not larger than or equal to 2, so I better not include 2. Okay, good. Notice there's a 6 in here, but I told you that the result wasn't 6. So I know this outcome couldn't actually have occurred. What I ask you for is the probability of getting a result larger than 2. But I give you more information. You already knew the result is not 6. So this notation, the probability the result is larger than 2, given that it was not 6. So this little vertical bar is read given. And so if there's you have some information, you can write an event which describes that information and put it after this vertical bar. So that tells me you're calculating the probability of getting results less than 2, the probability this event happened, knowing that this event n already happened. So you can think about it as we're just basically updating our sample space. It used to be this whole thing. Now that we know that 6 didn't happen, our sample space has really been cut down to just these outcomes. So there are 5 outcomes here. And I'm assuming that this is a platonic die, 1 in 6 chance of landing on each side. Then what probability should I assign to these? Well, it's equally likely to land on each side. And so if I know it didn't land on 6, it still seems equally likely that it should land on any other side, right? So I'm going to say all these are equally likely. So I have 3, 4, and 5, which are 3 of the equally likely outcomes in this event here, which has 5 equally likely outcomes. So I'm going to say that this probability of rolling a number larger than 2, assuming that the result wasn't 6, is 3 out of 5. It's these 3, right? Now, if you think about the way I calculated that, you can write 3 over 5 as 3/6 over 5/6. Why would you do that? Because first of all, I can do that because it's a fraction. I can multiply or divide the top and bottom by any number I like as long as it's the same on the top and bottom. 3 out of 6, that's these 3 outcomes right here. So this 3 out of 6 you can interpret as the probability of these 3 outcomes, the 3, the 4, and the 5. What are those? That's the intersection. That's the outcomes that are in both n and l. So it's the probability of L intersect n. Oops. And what's this thing on the bottom now? This 5 out of 6, well, that's just these 5 outcomes. That's the probability of n. Because this 5 right here, those were the 5 outcomes that could have occurred after I eliminated the 6. So in fact, we'll see in class that this is how you can define conditional probability. The probability of one thing given another is the probability both occurred divided by the probability the event that you're assuming occurred actually occurred. Yeah. Okay, let's do one more example to kind of justify this rule a bit. This is the definition of conditional probability, it turns out. But let's just make sure it makes some intuitive sense. So let's do another example. Let's suppose that we pick a random number, random real number, between 0 and 1. So my sample space is going to be all the real numbers between 0 and 1. So I can think of that. So I'm picking a number on the number line between 0 and 1. So I'll draw a little number line here, and put a 0, and put a 1, and I'm picking a random number somewhere in that interval. Let's define a few events. How about h? Let's let that be the event. The number is bigger than 1/2. So 1/2 is bigger than x less than or equal to 1. So this is the set of all real numbers between 1/2 and 1. So I'm going to put 1/2 right there. So if h occurs, that means when I pick this random number, it ends up somewhere here, between 1/2 and 1. And similarly, let's let q be the event that the number I pick is bigger than 1/4. So again, I'm going to put little divisions here, 1/4, maybe even 3/4. And so if the event q occurs, that means the number I picked was somewhere between 1/4 and 1, somewhere in here. Now what's the probability of h given q? Well, that's the probability that the number I pick is bigger than 1/2, assuming that I already know it came out bigger than 1/4. So what are we assuming here? That it's bigger than 1/4, so it's somewhere in this shaded area right here. So assuming that the number we picked is somewhere in that shaded area, what is the probability it's bigger than 1/2? Well, to be bigger than 1/2, it's going to be in this area, which I'm shading the opposite direction, right here. So the probability that the number is bigger than 1/2, assuming it's bigger than 1/4, well, if we're assuming it's bigger than 1/4, then it's going to be in one of these three little bits. The bit between 1/4 and 1/2, the bit between 1/2 and 3/4, the bit between 3/4 and 1. And because we're picking the number at random in here, it's equally likely to be in any of these three pieces. To be bigger than 1/2, it has to be in one of these two pieces. So it stands to reason that this probability should come out to be 2 out of 3, because in 2 of the 3 pieces, it's bigger than 1/2, and we're finding the probability it's bigger than 1/2, after assuming that the number landed in one of these 3 pieces. Let's check that our little definition gives us that I mentioned up here, gives us the same answer. So what if we do the probability of h intersect q over the probability of q? That should give us this 2/3. Let's double check. What's the probability of h intersect q? Well, h intersect q, that's this area I shaded twice right here. So the probability that when I pick a number between 0 and 1, it ends up in this double shaded part, well, is 1/2. And the probability that when I pick a number between 0 and 1, that it ends up bigger than 1/4, that q occurs, is this area to the right of 1/4, which is 3/4. And if you just multiply this fraction 1/2 top and bottom by 2 to make it into quarters, we get 2/4 over 3/4, and that's going to give us, yes indeed, this 2/3 that we expected.